think so. Yes. To go. Okay, thank you. Hi, everybody. Thank you for this invitation. Well, I will be more general, if I can speak in this way, than my previous colleagues. And I would like to begin this keynote by positioning the contribution within the context in which we operate. I will be assisted by my notes for your safety, so I will stay in the due time. We're a group of professors and researchers from Politecnico of Milano, working in the field of architecture and urban representation mainly. And for many years, our discipline has been grounded. Sorry, I did something wrong. To go back. Okay. In digital surveying practices and the subsequent representation of the built environment. And this journey evolved from the interpretation and redraw of mainly existing buildings based on point clouds, laser scanning and such activities, to increasingly sophisticated digital modeling approaches. With the advent of advanced digital technologies, our contribution naturally expanded towards point cloud-based modeling, object-oriented design processes, and the broader realm of BIM, intelligent representation, reliable digital description of architecture and cities. That is the base for digital twins also. With this background, our perspective on sustainability has always been intrinsically linked to issues of modeling and representation. We do not consider sustainability as a separate key, as a separate layer added to the design process. Rather, we see it as a necessary information that must be a part of a digital model itself. The challenge is therefore not only to measure for us sustainability, but also to represent it, visualize it, make it accessible within the digital environment where the design decisions are generally made, because we decide with what we see in general. So I'm honored to introduce the research team that I have the privilege of coordinating, a rich and stimulating blend of intuitive beta architects and alpha engineers, or perhaps alpha engineers, alpha architects and beta engineers, it depends on the topic. And result is that this diversity of perspective creates an especially inspiring and intellectual stimulating environment, at least for me and for the group. This is the main paper you will look at this afternoon, dealing with one of the topics. And environmental performance assessment is a crucial aspect of sustainable design. In spite of this, life cycle assessment is often introduced only in advanced design stages, when key decisions regarding materials and construction systems have already generally been made. This limits the possibility of effectively reducing environmental impact through informed design choices. To address this challenge, we looked for the integration, in this paper you will look at it, of environmental product declaration, EPD, with the BIM environments, enabling designers to access and interpret environmental information from the early project phases. The proposed framework aims to bridge the gap between design development and sustainability assessment by automating the connection between BIM objects and verified environmental dataset. The methodologies focus on the creation of a digital workflow capable of collecting, structuring, and visualizing the environment. In the first steps, in a systematic review of LCA integration in BIM, 4 findings framed our choices, mainly. First, the most consolidated approach is still the bill of quantities workflow, about 35% of cases, but it is largely manual and static. The second is that EcoInvent remains the dominant database, valued for considering consistency and traceability. Third, on communication, bar charts dominate around 60%. And fourth, analysis concentrates on modules A1 to A3, the product stage, as you know, where data is most available. Our assessment focus on embodied carbon in the product stage, covering raw materials extraction, transport to manufacturing facilities, and production processes. These modules are the most consistently documented with the current BIM LCA research and provide the most reliable environmental data. Together, these 4 points reveal a gap. The field is consolidated, but still manual, fragmented, and visually flat. And this gap motivated our workflow. 4 methodological decisions were defined the proposed approach. First, we adopted a direct link workflow in which the BIM model is coupled with the APDs so that environmental indicators are updated in real time as the design evolves. So this is one of the 4 researches I'm going to show you. Second, we select EcoPlatform as the reference database owing to its standardized, harmonized EPD data and its open source nature. Third, we concentrated the analytical scope on the product stage in the model A1 to A3, where data availability and reliability are the highest. And fourth, we adopted 3D parametric visualization, that is our aim, in which environmental performance is represented spatially with within the design model. This is the full pipeline in 5 steps. As you see, we start always from the representation of the models and from the survey of the existent. So we begin with a geometric acquisition. We use BLK2Go, laser scan from Leica and others, modeled in Revit or other platforms, but here Revit. Second step, the data template structure according to ISO 22057, the standard data dictionary for LCA and APD. This is the semantic backbone that makes every material speak the same language. In the third step, the APD pre-processing was pre-processed in Python with pandas, NumPy, and regular expression to clean, normalize, and harmonize heterogeneous dataset. For the fourth step, we automated population. Dynamo writes the parameters back into the platform, Revit, element by element with no manual entry. So this is an automation of the process. And finally, GWP, visualization, so global warming potential, is color-coded directly and simultaneously on the 3D model. So carbon hotspot became visible to designers from the beginning inside the design environment. The key idea is that environmental data becomes an explicit traceable parameter of the model, not an external report, not a data that comes from outside and you have to look at it. Remember that we have a starting point in visualization as our research topic mainly. So looking at the strength and limitation, the strength is that Dynamo plus Python automation removes manual insertions, so we avoid errors and make the pipeline reproducible. The designer only assigns material that are normalized. Also, real-time in-model color coding reveals hotspot with no external software, so it is inside the platform. A dual scale metric per cubic meter and per square meter of floor area support both element and building level comparison. But there are some limitations, of course. The limitation, EPD data is still heterogeneously across operators, so a human check is needed at the beginning. Full automation is not yet achievable at this point. The scope is limited to embodied carbon, A1 to A3, so this is not yet a whole life. And we are still in a proof of concept of some cases, so scalability is not yet totally validated, but we think that we are in the right path, sorry. And color simplification must always be paired with explicit uncertainty, so we do not overstate an early stage estimate. So according to this work, we started to enlarge the experiment to larger areas, and we started also to paint it with other experiments. This second research extends the application of the digital twin methodology to the urban scale and deals with a research on frugal digital twins for indoor air quality management. The starting point is very simple, and this work takes the digital twin methodology, which we usually apply to a single building, and pushes it up to the scale of a whole simple settlement. That is this place. The case study is a small hamlet in central Italy. It was chosen for a very practical reason. The built heritage there is remarkably homogeneous. The masonry is very similar right across the village, and the whole settlement can be treated as one coherent fabric rather than a collection of unrelated buildings. So it's a simple example, let's say. That homogeneity is what makes the framework as shown through the next few slides. The first stage, yes, is about building the ground where the settlement sits. We want to represent it. So what we call the territorial canvas where we lay with the buildings. We create a high precision terrain model using only free available cartography data. This is deliberate. The method has to stay low cost, frugal, so anyone can reproduce it without expensive survey. The digital terrain model is discretized into a cloud of points inside a GIS system. These points are then processed in Grasshopper to generate a continuous NURB terrain surface. So we want to visualize it. On top of that, we build the model of the built-up area by taking the outline of the buildings and projecting them down onto that continuous NURB surface. The result is a faithful base model of the hamlet in its real landscape. Sorry for this. Sorry for that. The workflow shown explain how starting from a rhinoceros building model and using the BIM plugin NURBS geometries can be converted into BIM entities, which can be used to create a digital twin model. It's a wrong slide, sorry. Here is shown the digital workflow, how we move from a plain geometric model to something more intelligent. We start with a building model in rhinoceros, then using a plugin called BIM, we convert those NURBS geometric into BIM entities. The conversion is the key step. It is what turns simple surface into building objects that can carry information. And the BIM entities are what lead us build the actual digital twin in the next stage. So the takeaway here is direction of built environment restriction from geometry to BIM to the digital twin then. This is a topic that we face always. I mean, we have as modeler different possibility to model buildings and model buildings with information, but our what worries us that we would love to mix information in every modeling environment that we know, not only in BIM platforms, but also in others that are more frequent, at least in those last times. Here we can see the process from the previous slide actually happening. This is where a geometry with no material properties become an entity that is rich in information. First, what we saw before. Rhino's nerve surface are imported into the BIM environment through Rhino Inside Revit interface. These are the platform we are using now. At this point, they are still purely geometric. They have shape, but they are not endowed with non-geometric data. To fix that, we use the Beam plugin which works inside Grasshopper to assign material and energy properties to those primitives. Finally, each individual hosting unit is given the stratigraphy, the layered wall built up. That's typical of this urban fabric. And because, as we said at the start, the masonry is so consistent across the village, this let us define a single permeability profile for the hamlet as a whole. That's what makes the settlement scale model realistic. In this final slide, we see everything together. We apply the full digital twin process to one typical building so that a residential can actually monitor and improve the comfort of their own home. The diagram, this is a diagram, of course, shows the framework as 5 layers stacked from the ground up. The layer 1 is the foundation. The NURB wireframe mesh, the geometry we have built up over the previous slides, tied to the terrain through the GIS BIM integration. In the second layer, the brain, a network of low-cost Arduino sensors monitoring temperature, humidity, and CO2 levels in real time. In the layer 3, the interface, a LED dashboard. It displays the sensor data, shares it with a cloud-based management system, the digital shadow up in the cloud, and warns the resident when, for example, CO2 gets too high. The layer 4 is the actuator, so the response. Prompted by the dashboard warning, the residents simply open a window to ventilate and bring the CO2 back down. The person stays in control of their own environment. In the last layer, the lounge, a biophilic layer, we call it, a specific plant species, golden photos, a P frenum aurum passively absorb CO2 and produce oxygen, and the model monitors how much it offsets. This project was funded by the PNRR funding by the European Commission. So there are many future researchers. I'm not looking through that. And only I would say that for whole life assessment, we will extend to the use phase, end of life, and module D to reduce manual effort. And we are exploring also AI and natural language processing to align multi-language APD fields. Because growing in these fields, we are looking at the possibility to interface and to let more platforms to interface one to the other one. And we have two opinions in the group. One is still saying that we can do that with computer science. The other one is saying that the processes to harmonize data are becoming too complex among the platforms, and we could be assisted by AI. But on this point, we are really in an early stage. I'm going to show you something now that is really only an idea we're working on. In fact, the semantic orchestration for environmental workflow in AEC is a topic that we need to face. Because the information we generally have, EPD and other, already exists. Every construction product has an environmental product declaration, the EPD, with its global warming potential measured and published under the rules. The data is there, but it is scattered across format and languages, and it lives outside the tools where design decisions are actually made. So, environmental feedback comes after the geometry is fixed, when the choices that matter most, the material, the assembly, the massing, have already been taken. As you see, the goal of our group is to move that feedback earlier into the moment of the design itself. And there is no one single tool, there are several. A real project moves through many authoring tools, from the building model, visualization engine for communication, civil tool for the road and for the terrain, grasshopper, computational design, a survey platform, different laser scans, so many. These tools do not share a common notion of what an environment property is. So even when the data has been cleaned in one of them, that work doesn't transfer to the other most of the time. And each tool becomes its own environment, its own island. This is the gap the research we are starting now addresses, but it's only an idea, let's say. The heart of it is we want to give a simple instruction, attach the material's carbon data to the element that carries it, and what the element that carries the material actually is in each tool should be transferred to the other one. In an authoring tool, it is a real building object, something you can select, tag, and query. In a visualization engine, it is only a surface sometimes, appearance painted on a mesh, and not an object or a building, just a part of it. In a civic tool, it's a slice of a road corridor, for example. In a survey platform, it is a measured surface or point cloud captured from the ground. Some words for incompatible realities, a polymorphic element where reconciling is the scientific core of that work. So there are two levels of harmonization, we say, and they are complementary from our point of view. The first data is harmonization, making the EPD data itself clean, consistent, and usable inside one tool. And that is the pipeline you saw before. The second is operational harmonization, making the same environmental operation execute faithfully across every tool. Can computer science do it? Or can AI help us to do it? Same logic, one level up. One works on the data, the other works on the platform. A fair question is whether existing standards already do this. Well, I'm not going deep inside that, but we want to look in filling three gaps that becomes three questions. We are in the early stage of it. First, how can a single environmental concept be represented so that it is correctly interpreted across tools with fundamentally different data models? This is the challenge of a semantic reconciliation. The second, how can a designer express an intentional once and have it consistently encrypted across all platforms without manually scripting each tool, because scripting is a bit complicated. Third and most important, how can this process incorporate an AI agent while preserving the trustworthiness, traceability, and reproducibility of our environmental data? So we are in an early stage of this work, so I'm not going in deep inside, but we think it's a good view for the next steps in our group, at least. I'm shortening a bit. We are speaking of a translation layer. So the designer make in the future a request in plain language, and the AI orchestrator we are looking for interprets it, reasons through it, and turns it into a sequence of shared verbs. The common vocabulary keeps the meaning consistent, while each tool-specific connector translates that meaning into action inside Revit, Blender, Unreal, Civil 3D, or Survey platform. This is our intent. This is where the layer complements existing standards instead of duplicating them. IFC, OpenUSD, and ISO rules define data at rest, how information is structured inside and between tools. The translation layer should operate live across running application. It orchestrates action, aligns concept across platform, and bridges meaning that no single standard can fully cover. Take this as an idea we are working on, but just to say we're going in that direction. An AI agent can be unpredictable, while environmental data must remain reliable. Therefore, the agent is constrained by 3 control mechanisms we are starting to look at. A canon, only verified facts from certified APDs are accepted, no invented values, all calculation must reconcile across scales, from layers to elements, and from elements to the whole building. A deterministic quality gate, an independent checker must verify that every material has a valid documented APD and unit conversion, and a human, of course, loop supervision that is necessary in any case. What should this give us? The contribution could be a semantic and operational layer that sits above existing standard and makes environmental reasoning portable across tools, not locked into one. It is complementary to the LCA integration work in our group. The pipeline should prove that the data can be trusted, and this framework let that trusted data act everywhere. We see what happens in the future. To conclude this presentation, that is very various, but we wanted to show you what we are working on, even if sometimes in an early stage, because we deal with visualization of model and we deal with sustainability. One point is that sustainability in our hardware, let's say. One of the reflections currently guiding our work concerns the sustainability use of existing equipment, our equipment. And it seems a small thing, but it is not, because AI is just eating our memories, and we are looking at that. In particular, we need, as visualizer, to extend the lifespan of hardware, ensuring its use for as long as possible in order to maximize its value and reduce environmental impact. That is a common problem. I've just finished 2 minutes. Working on digital models, this work asks a simple question: can we keep doing photorealistic heritage or other visualization without buying new hardware? Yes, the research project is Pixel VR, because since the recent AI boom has redirected global memory production, DRAM prices have more than doubled, and AMD skyrocketed up to 246%. NVIDIA is cutting GPU production, while photogrammetric dataset keep growing into hundreds of millions of polygons. That is a problem that we have. This is the RAM price curve, mainly flat for years, then rising vertically from late 2025. The same graph trend for graphic cards that we use a lot, and for the storage of our data. Meanwhile, on the demand side, even a small scanned object at high details produce millions of polygons, and we need them to visualize. A full building survey, hundreds of millions. So realistically, processing these unoptimized dataset may require over 6K euros of components. After our optimization workflow, we were able to use 500 euros of used hardware to optimize these datasets. Our benchmark is a Dell laptop of 2020, running the pipeline, save a lot of money, of new workstation spent. So very briefly, how the pipeline works in terms of visualization. 4 design principles: aggressive but fidelity-preserving reduction, full automation of most of the stages, exclusively free open source software, a low RAM mode, so 8 to 6 gigabyte machines finish instead of crashing. 5 automated stages inside Blender, cleaning, remeshing with instant meshes, curvature-aware decimation, UV unwrapping, texture baking from the original high poly source. And the result, across 5 datasets of very different scale, we had a polygon reduction from 98 up to 99%, with texture memory cut by up to 99% as well. Well, the original on the left, optimized on the right, the result is quite nice, almost visually equivalent. The perceived detail is carried by the baked texture, not by the polygons, and even at close inspection, the optimized model holds up. And the same result on the largest, most complex dataset. Beyond the economics, this may be part of the circular transition in practice. So extending hardware life differs e-waste with 0 material input, what the EU Circular Economy Action Plan calls for. To conclude, viability is set by software, not by the hardware generation. Optimization turns impossible dataset into trivial ones, saves thousands of euros for seats, and keeps existing machine productivity. Thank you for your attention. Sorry if I read most of the time, but the schedule is short, and this is my possibility in this case. Thank you so much.
Thank you so much. Thank you so much for insightful presentation.